What if there was a world where we didn't have to worry about harsh chemical reagents and toxic waste when producing the pharmaceuticals we need for our day-to-day lives? Is there a world where we can create safer chemicals that take less energy to synthesize? Green chemistry aims to solve these issues. Green chemistry is an initiative to develop greener chemicals, processes, or products through 12 principles, designed by Paul Anastas and John Warner. Principles such as one-pot synthesis, the use of catalysts, and solventless reactions are being tested for their viability in pharmaceutical production. Using these principles, researchers are developing new ways to synthesize drugs and to produce medications more sustainably. But how does this matter to the average man? With the help of green chemistry, costs associated with costly reagents and solvents can be eliminated. This, in turn, lowers the overall cost of producing the drug, often by at least 50%, sometimes more. The lower cost of making the medicine means the medication's market price also decreases. With lower prices, more people have access to drugs who would otherwise be unable to afford today's exorbitant prices. In addition, solutions found using green chemistry are not only more cost-effective, but also more sustainable and environmentally friendly. By creating energy-efficient reactions, drug production becomes more sustainable and viable. Likewise, using fewer toxic chemicals results in less waste per synthesis and makes each procedure eco-friendlier. We are beginning to see advances in drug production through green chemistry. One area of drug production where there are promising results in the research is an alternative synthesis of the anti-malarial drug pyronaridine. The need for pyronaridine is seen heavily in Africa, as over 300 million people need the drug. Yet, the current pricing of the drug means that only 2 million can afford it, leaving millions without treatment. To solve this problem, 2 new routes were sequenced, each of which takes advantage of green principles. For these routes, scientists working for Medicines for Malaria Venture emphasized the synthesis of pyronaridine, which relied on water and environmentally friendly, non-volatile solvents. When the yields of the newly sequenced linear route and the literature linear route were compared, the new route yielded 95%, whereas the literature route yielded 69%. This can be attributed to the greener processes used and the reduced reliance on volatile chemicals. While it remains to be seen how the market price of the drug will be affected, the use of green chemistry has enabled a more efficient route to the synthesis of the anti-malarial drug. Another research section that shows encouraging results is the synthesis of oxidiazol derivatives. These heterocyclic compounds show promise in multiple medical applications, including antimicrobial, anti-cancer, and anti-inflammatory agents, as well as potential treatments for neurodegenerative and metabolic disorders. These derivatives are used in a wide range of medicines and are becoming essential to drug production. Recently, accelerating the synthesis of these derivatives has been explored through photochemical reactions and ultrasonic irradiation. Photochemical reactions use infrared, visible, and ultraviolet light to accelerate reactions without adding another reagent. Photoactive compounds are electronically excited and undergo the reaction in their excited state, which produces a more efficient reaction. This technique is considered an eco-friendly approach to conserving energy while minimizing waste. Ultrasonic irradiation yielded 78 to 90% product in a shorter reaction time than those required by conventional heating methods, which require 15 to 20 hours of refluxing. Other benefits of green chemistry beyond the decreased cost of reagents and the reduction of volatile solvents. These include creating inherently safer reactions for accident prevention and energy-efficient synthesis techniques. Safer reactions mean less danger in the lab for medicinal chemists. There is also a lower health risk for these medicinal chemists because there are fewer volatile and toxic chemicals in the lab. Energy-efficient synthesis techniques provide another avenue for developing sustainable reactions that have less of an impact on our environment. In addition, energy-efficient synthesis techniques would allow us to run more reactions with the same amount of energy required by an inefficient reaction, increasing the total yield of the product. However, no initiative is perfect, and green chemistry does come with disadvantages. The initial cost of green chemistry alternatives is found to be higher than that of the typical procedure, due to the need for new equipment and the development of new methods. In addition, it may be challenging to scale up processes from a lab to industrial scale production. Finally, some greener alternatives may not be as efficient as their industry standard counterpart. This, coupled with the other disadvantages, shows some limitations to green chemistry and why the initiative is not the industry standard. So, what is the future of green chemistry? In the coming years, we can expect to see more research papers publishing techniques and sequences that use green chemistry. Eventually, these techniques will reach the industry level, and the effects of the change will be seen in drug yields and costs.